Okay, so this set of videos is going to cover chapter 12 of a textbook by author last name Malik, C++ programming. So chapter 12 covers pointers, primarily it covers pointers and virtual functions. So we'll talk about virtual functions in a few videos, but for now we're going to talk about pointers. A pointer is a data type. A data type has a pretty common sense meaning, but you could define a data type that's consisting of two things: a set of values and a set of operations upon which you can a set of values that you can perform on a given value. Integers, you can perform the typical arithmetic operations: addition, subtraction, integer division, and multiplication. You can also perform the mod get the remainder of two operands. Odd mod 4 is equal to 1. Doubles are an example of a data type for which the mod operation is usually not defined. 5.4 mod 3 will generate an error if you enter this value in C++. If you attempt to perform this operation. Expression must have an integer type. Okay, so we have a good idea of what data types are. The pointer data type is a data type whose values are the memory addresses. The value of a pointer must be a memory address. We can't set a pointer equal to an integer, a double, a character, a string, a character array, an object of the car class, for instance. We can't do this. We could set it equal to the address of an object of the car class, but pointers, to define them simply, pointers are variables whose values must be a memory address. So we've seen memory addresses before using debugging. If I debug after setting a breakpoint and I come to the debug windows and look at the contents of memory, I'll be doing this a few times in this video. Look at the contents of memory. At the moment, I have a local variable. This is the locals window pane right here. And we're interested in the contents of memory. So if I type ampersand A, the address of the variable A, and I step to this instruction, step one more, you see the variable A has the value 02000. That's 4 bytes. So we've seen memory addresses before. The example of this in this example, the memory address, the address of A is this hexadecimal value. Hexadecimal memory addresses are generally precluded or appended by, set off by a 0x that indicates hexadecimal. And this F here is also a giveaway that this is a hexadecimal value. We may not be familiar with the base 16 number system yet. Humans pretty much always use base 10. If we switch to programmer mode in the Windows calculator, you can see the value 16 in decimal has the hexadecimal value 10. It has the binary value 10000. So just a very brief introduction to hexadecimal. Memory addresses in computers are often indicated using hexadecimal like this. This is a memory address. So, okay. Let's get into declaring pointers. So the pointer is indicated using the asterisk. A pointer type is indicated using an asterisk. It is not the multiplication symbol. So if I want to set a pointer to A, that is print the memory address of A, we have the operator ampersand. The ampersand operator this can be read address of A. The pointer to A is equal to the address of A. So the ampersand, that's how you might read this. Okay, so this is legal. This is illegal. Cannot set a pointer to an integer equal to an integer. This int star, a value of int of type int, which is this A, cannot be used to initialize a pointer to an integer. Ampersand is necessary here. If we remove the asterisk and set pointer to A equal to A, this is legal. If we print pointer to A and we print the address of A, that we'll see two lines of output that are the same as one another. See something FBA4 FBA4. I say something because it's not terribly important. If you switch to 32-bit mode, you'll notice a change in the output, the memory addresses, the length of the memory addresses. We have 1, 2, 3, 4, 5, 6, 7, 8 digits. So this is 32-bit. So each digit is a byte. So 8 bytes times, each digit is 4 bytes. So each 4 bytes each, 8 bytes total. Each digit is 4 bits. So 4 times 8 is 32. Okay. And what am I talking about? How did I arrive at this assertion that each digit is 4 bits? The maximum value in each position is F. It's that base 16 business. So 1, 0, and 1, 2, 3, 4 bits are needed. The value 15 has the value F in hexadecimal. I'm not trying to explain this from first principles, so to speak. So I'm just trying to give a loose idea of what's going on here. It's best to approach this in a computer organization class, or to approach it from what I call first principles. Okay, so that's our first pointer. If we declare a double variable, pi equal 3.14, and we attempt to declare a pointer to a pointer to pi, if we do so with an integer type, this is a problem. So int star pointer to pi equal address of pi. We see a double pointer cannot be used to initialize an entity of type integer pointer. So this needs to be doubled. Similarly, if we make a car object or a car struct or class, we make a car object C, and we attempt to declare a pointer to the car object using int star. This is a problem. See a similar error. A car pointer cannot be used to initialize an integer pointer, but we can declare pointers to objects. So the address of this car object. Okay. And this is actually very useful in something called linked lists, or nodes of a linked list. But we'll talk about that later. Linked lists naturally use pointers. We'll talk about it in data structures and algorithms class. Okay. So this isn't a big deal, but some people talk about what is the most reasonable position of the asterisk. If it's here or here or here, is there any difference? All of these programs will not generate syntax errors. Let's see. Let's comment out the I here. So we're printing the pointer to A and the address of A, and notice I've got the asterisk in the middle here. It's not touching the T or the P, so to speak. You know, a lot of the time spaces matter in programming, but it doesn't matter in this case. So put it where you like, the asterisk. And again, it's not multiplication that's happening here. What happens if we put the asterisk right here? This is a problem. So don't put it there. Okay. Hopefully that's not confusing. If you're declaring multiple pointers on the same line, just declaring multiple pointers on the same line, I think this is the way to do it. Yeah, if you this might be something somebody's inclined to do. This is not going to be a pointer type. If I try to set pointer to C equal to the address of, I haven't made a C yet. I made a C called car, but I commented it up. If I say int C and then I try to set this equal to the address of C, we see that this is a pointer to an integer, but pointer to C is getting regarded as an integer because I didn't put the asterisk right here. Okay. Anywho, nothing. I debate even talking about that because, but I think it bothers some people, the space here or the put the asterisk there. I don't really care about it very much. These C style arrays, the static arrays that we have, that people pretty much always talk about in a first class in programming. They have a relationship with pointers. So this relationship between what are often called C style arrays and pointers. This asterisk is acting as the dereferencing operator here. So the result that we see when we run this program is fairly interesting. We see a 1. We change this to an 11. We see an 11. So these can be, this raw array can be referred to as a pointer in disguise, and it has been referred to as a pointer in disguise by certain people. But I paused for a while there because I realized I was jumping the gun a bit. I'm looking at my slides over on my second screen, and I mentioned an array, but I was thrown off by the order of my content. What I was demonstrating was let me demonstrate what I was trying to demonstrate with this slide right here. So if we run a loop 10 times and we declare some array of integers, and we print the address of each element of the array, not the address of some array, but the address of each element of the array. What do we see here? We see memory addresses that step up in increments of 4, 0, 4, 8, C. So C might be confusing, but in hexadecimal, 12 has the value C. So if we perform some arithmetic here, 8 plus 4 is 12, of course, but in hexadecimal, the value 8 has the value 8. 4 has the value 4. In binary, it's 0, 1, 0, 0. But 8 plus 4 is equal to 12, plus another 4 is equal to not 16 in hexadecimal, but 1, 0. So notice that this is a 3. So 3C plus, let's just do this. 3C plus 4 is equal to 40, except it's not 40, it's 40. Okay. I have to be careful not to get into hexadecimal number systems too much. I do enjoy that content, but similarly, 4C plus 4 is going to be equal to 50. Okay. All right, this demonstrates I was mixing. I'm typing this on the fly, so it's not a surprise that I did something a little bit silly there. There we go. That warning goes away. I went beyond the bounds of the array here, and that demonstrates another weak negative aspect of these C-style arrays or raw arrays, static arrays. Using standard array is not something I've talked about yet, but I usually hold off on talking about this until we talk about data structures. But the preferable alternative, just to go ahead and mention this, is not strongly related to pointers. Is to use pound include array and declare a standard array from the standard library. Suppose this is as good a time as any to mention this. Now, if we print the address, if we run too far, we run out of bounds here and we print the address of some other array, which is a standard array. It's not this thing called a raw array or a C style array. It's called a C style array. We are writing programs in C++. C style arrays are the array, it's the way you declare an array in C, the precursor to the C++ language, which is possibly less safe in some ways. But whenever we run out of bounds here, I think we trigger an assertion. No. Excuse me, I was printing the address of the first element there. If we include the iterator, we hit an assertion after the fifth element, so the array subscript is out of range. So it's actually recommended to use this array type, but I suppose because of textbook tradition and the influence of the C language, we generally go into this first. Okay. But back to arrays and the dereferencing operator, we have seen let's run until, let's not go out of bounds there. Not that it generated an error with the C style array. Memory addresses, examples of memory addresses are right here. And I am still 32-bit if I want to change this and see more digits, which, that's not my motivation here. This is a bit more difficult to read. Why would we use 64-bit instead of 32-bit? That, I guess I'll defer that question. That's getting too far afield, I think. Okay, maybe the answer is obvious to you. I do have a slide that makes reference to this show base and hex business. So that is perhaps a nice thing to see. Since we're talking about number systems, you might have interest in doing this. So if we print the array contents, and let me remind you of what happens if we go out of bounds and we print the array contents. See these garbage values, what are often called uninitialized or garbage values. So what happens if we say cout show base? And we specify hex, not decimal, not octal. I'm not sure if binary has an option. It certainly has an option somewhere, but I might mention how to do that later. We specify output in hex. Notice we're generating this warning now. I see 0xb, 0x2, 3, 4, 5. So the hexadecimal value B has the value 11. So, okay. And then those uninitialized values, it's worth noting that that's CCCCC. Okay. The accessible on the subject of memory, This is a nice thing to see if you click these buttons after you've set a breakpoint. I'll just set a breakpoint on every print. Not strongly related to pointers, but it is getting into some nice detail. Windows, show diagnostic tools, settings. When the dog's barking. Settings, the gear icon. You can see how much memory our program is consuming, which is a nice thing. But if you come to the diagnostic tools property pages, you can see the default on my machine is 20% of the disk usage for memory. Virtual memory usage is 8 gigabytes. So you can increase this if you want to. So it's just a nice thing to be aware of. That I enjoyed putting in my slides. Okay. And I mentioned this earlier. Pointer, why is it called a pointer? This text supplies some reasoning as to why it's called a pointer. Okay, but now the dereferencing operator that I mentioned right here. So if we just stick with a simple data type for the moment, and I remove my print statements or comment them out, we say int a equal 5, int star pointer to a equal address of a, and we say cout asterisk, not a, but pointer to a. So what is this? Expression operand of dereferencing operator must be a pointer, but it has type integer. So that's saying you need a pointer type here, pointer to a. Of course, you can do 5 times 4, and that is legal. That prints 20, but this is a unary operator. It takes one operand, and the operand must be a pointer type. So if I this says get the contents of the address, get the contents of this address. So the pointer to A's address, its value, dereference, to put it in a fancy way. So the contents are 5. If we update the value of A and we say A is actually 6, and we print again, and we maybe say before and after. So A is initially 5, and then it's 6. Okay. Okay. Says a picture of what we just did, or something similar. This is bit of an that's pretty atypical. It's interesting to see that this works. Yeah, this is our what we usually call a notation, the subscript operator, the index operator. We usually associate it with arrays. What happens if we put in a 1 here? Natural question to wonder. We see a garbage value, but that's pretty unexpected. this operator won't work on a, I don't believe it works. Yeah, it doesn't work on this type, the integer type. But if you wanted to do this, you could. And that gets to the what I was showing down below, the relationship between this C style array being a pointer in disguise. But yeah, we can use this notation also. Pointer arithmetic. So pointer arithmetic, it's probably nice to show using an array. Maybe we omit the loop. So we say pointer arithmetic involves addition and subtraction, except it doesn't work in the way we perhaps expect it to. So the pointer to A has some value. It's the memory address of A. And if we print the initial value, it's going to be a memory address. And if we do some pointer arithmetic, so we say pointer to a plus plus, first off, is this allowed? Can we add 1 to a memory address? And what does it mean to add 1? Are we adding 1? Let's take a look and maybe it makes sense. So we've gone from F4 to F8, a memory address with a bunch of digits, and it ends in F4 and then F8. So adding 1, we haven't added 1 to this memory location. We've added 4 because the pointer type, the integer type, is 4 bytes. If we change this to double, and then double, and we add 1, so to speak, we step forward 1 position, we have E8 and F0. So what is the what does this look like in Windows calculator? What is 6F0 minus 6E8? 6F0 minus 6E8. It is 8. Okay, so 8 hexadecimal. And 8 in decimal, and in octal 8 has the value 10, and binary it has the value 100. So there, hopefully that makes sense, and it reinforces the notion that doubles are allocated 8 bytes of memory. If we increment twice, we go from 4.8 or from 3.8 to 4.8. If we decrement or add 2, pointer to A equal pointer to A plus 2. This is an alternative way of stepping through an array, raw array. So we see 9.8 and 8.8. Hopefully that makes sense. If we add 4 or subtract 4, we're going to step forward 5AC, 5C8. Okay. Again, I'm not so concerned about hexadecimal arithmetic in this class or pointer arithmetic. I'm just showing it. It's regarded as a bit of an unsafe thing to do nowadays. There's something called smart pointers that are the that are more strongly advocated nowadays in modern C++. Okay, let me comment this stuff out and hide it because I'm getting distracted by it, and I expect the viewer might be as well. Okay. So I just mentioned smart pointers, and nowadays the use of new and also delete these keywords is it's maybe unlikely to see this in industry. It depends what company you work for, but I think seeing this still has some value. We just need to be careful not to generate memory leaks because that is a potential problem with use of this thing called new. So new does these two things. It returns a memory address and it allocates memory. Okay. So this is related to something called the heap, which I haven't dug into it in a great amount of detail. So I'll try to limit my use of the terms heap and stack. An alternative way of creating a pointer is to say something like this. So now if we print pointer, we print a memory address. Let's change to 32-bit. Maybe it's just nicer to see. Okay. So we see some address, we could increment, we could add one. The pointer doesn't currently have a value. There is no value, the value is uninitialized. So let me, if we do reference, if we say cout, this is uninitialized value. So can we say this? Is this legal? It seems so. We printed 54. Okay. There are potential uses of this. We can see this from the perspective of the memory as well. Delete. So to motivate delete, might be nice to go ahead and show a memory leak. So I'm going to open up my task manager and show, we'll stick in this view. And we want to keep an eye on this number right here, the amount of memory used by Visual Studio. And it's increasing very, very quickly. So this is becoming something like okay. So it's over 2 gigabytes of RAM. So this is an example of a memory leak. And we think, let's see, let me stop this and check it there. Look at the contents of my program. Okay, I was a little bit surprised that we hit bad memory allocation, but as you can see, the amount of RAM usage is very large. We ramped up to 2 GB, so the bad allocation exception, I was a little surprised that we hit that, so I was pausing for a minute to take a look at that. But this is leading to what's called a memory leak, where in an infinite loop, we're asking for more and more memory. So if we delete on every loop iteration, if we delete the pointer, then this is not asking for infinite amounts of memory. And now if we look at the task manager, the amount of memory is not ramping up without it's bounded by the operating system that I'm using, and it's bounded by the settings. If we go back to diagnostic tools and settings, there is a maximum that this is capped to. And usually when I run the program with this commented out here, I see it ramp up to 8 GB. So I was a little bit surprised by what we just saw, but anywho, yeah, we're remaining steady at less than 1 GB. And you can see that amount of memory being used. So kilobytes, 8,000 kilobytes is I think this is interesting that it's not an 8, obviously. Anywho, use of the delete keyword. Whenever we use new, it should be matched by a delete. So what does delete do? So deallocates memory. Allocation is a fairly fancy word to allocate. So what is the definition of this word? What is a definition? It's kind of uncommonly used to distribute resources for a particular purpose. So in this case, deallocate, this command is returning memory to the operating system. Okay. This asks for memory. The new operator asks for memory for the program. What's the difference between this? So asking for 4 bytes of memory, this is called static memory allocation, and this is called dynamic memory allocation. And I'll try not to go into too much detail regarding the differences between these two. These are two different ways of doing a similar thing. There are definitely big differences between them. And we'll explore those differences pretty naturally. We want to be careful that we don't do something like this. So let's demonstrate this and remove the loop. Tempting to call delete twice. So this throws this exception, access violation. Okay, if we comment this out, comment out the second delete, our program works as expected without throwing any exceptions. And I give some text here that talks about the motivation for using new and delete. Again, nowadays, these things called smart pointers are recommended. If you write code professionally in C++, you'll learn all about these things called smart pointers. It's not necessarily the case that you will go into C++ in a deep way. Okay. When the number of inputs isn't known before program execution. So the classic example here is the use of an array. You can't say cout enter desired array size. And then say int some array, declare an integer called array size, and then read in the array size and pass it inside the subscript operator. You over here and you see expression must have a constant value. Okay, so even if we try to use the const here, this is not allowed. You can't prompt the user to change something that's constant. You can set this equal to 5. If you try to update it to 10, this is a problem. Must be a modifiable L value. You also can't prompt the user to update it. So this is a problem, but the use of the new operator is a way to get around this, so to speak. Not get around. This is static allocation. It's allocation on the stack, on stack memory. It's not heap memory. So there is a way to allow this, and it's one of the most classic uses, demonstrations of the usefulness of the keyword new. So if you prompt the user, let's remove the const modifier. If you prompt the user, if you initialize, let's not even initialize the array size, let's just declare it and then read it in. And instead of this syntax, which is what we're used to, we could say int some array equal new int okay. So now if we use a loop, let's prompt the user for enter and then maybe after we're done, we echo their values back at them. So this can be quite convenient. The desired array size may be 4. So 3, 2, 1, 0. Okay, and we print 3, 2, 1, 0 back at them. So we have dynamic arrays now. This is one way of implementing a dynamic array. We've talked already, to some extent, we've talked about something called vector in C++. Vector is a dynamic array. This is a static array. This is a dynamic array. Dynamic means the size of the array can change. It can grow and it can shrink. We could, after prompting them for the desired array size and then reading in the values, we could say update array size question mark. We can change the size of that array. Let's just assume that the user might want to do that. Enter the new size of the array. And let's assume that the new size is larger. We can read in array size again, and then repeat this process. So this is dynamic, it's changing. And we will overwrite the previous values of the array in this case. Enter the desired array size, maybe it's 4 again, like the previous run. 4, 3, 2, 1. Okay, 4, 3, 2, 1 gets echoed at me. Enter the new size, maybe it's 10. Okay. And maybe it's 9, 9, 8, 7. Let me maximize my window. 7, 6. Okay, so you can see we've gone beyond our array is grown now. 5, 4, 3, 2, 1. Okay, and I hit a breakpoint here, so maybe I went out of bounds there. But you get the point. I think that's that error, whatever it was, is okay. Reading invalid data. It's not a huge deal. I say it's not a huge deal because we don't necessarily need to reinvent the wheel. Vector exists, and it is a nice way to do what I was just attempting to demonstrate. Okay. You probably have curiosity about heap versus stack memory. And if you take a class on the theory of operating systems and get into memory management, you may learn some more things about this. I've yet to dig terribly deeply into this subject. Okay, here's another example of dynamic arrays that wasn't just made up on the fly. Except here I'm not prompting the user. I'm also using the pointer arithmetic. It's kind of interesting to note that this syntax is allowed. Using the subscript operator right next to the open brace there. And this is more in line with what I was just doing. This was not allowed for static arrays. 2D dynamic arrays, I'm gonna skip this content. It gets a pointer to a pointer. That business gets a little bit unpleasant. So I'm just gonna delete those slides. So yeah, I mentioned that I'm gonna skip I'm not gonna get into pointers to pointers to pointers to pointers. You can make a pointer to a pointer, and you can make a pointer to a pointer to a pointer. So you'd be using int asterisk asterisk. That's a pointer to a pointer. And that's one way to make two-dimensional dynamic arrays. We've encountered two-dimensional arrays like string game board, an 8x8 grid, a matrix. So this could be something, if you're familiar with chess, like the A1 position. Let me bring up an image. So the A1 position is the white rook, B1 is the white knight, B7 is the starting position of this pawn here. Let's go over to the other side. F8 is the starting position of the king side bishop here. So a game board could consist of the strings. A1 is the 0-0 element, and E1 is the string E1 gets set to, let me put this in this notation, 0, 5, or 4 is equal to E1. And this is an example that we've seen before. At least I haven't put that in a video yet that's on this channel, but we could imagine this a two-dimensional array. And if we, in the case of a chessboard, the board is not going to shrink or grow, so we wouldn't use a dynamic two-dimensional array there. But there are certain applications, none immediately comes to my mind, where you might want an array who's a two-dimensional array, in other words, a matrix, loosely speaking, a two-dimensional array whose the number of rows and columns can grow. An example that comes to mind is a data set. So this is an array of data. A matrix of data. I'm not going to fill it out completely. So this is a matrix of data. You could represent it using potentially the data types are mixed here. So you might want to use a class to represent each person record. But if you wanted to if you all of a sudden just decided that you wanted eye color as well, then you would need to insert an additional column. You would need to change this 8 to a 9, so to speak. I know I'm mixing up my examples here, but yeah, and if you wanted another person to be in this matrix as well, you would add a row. So in that case, you would increase that 8 to a 9. You couldn't do that with static arrays, but you could do that using the new operator. I hope that makes some sense. I know I'm not going through it in great detail. But in that case, instead of using this pointer to a pointer notation, I would be more inclined to use a vector of vectors. And make sure you close this. So maybe we call this dynamic matrix, and dynamic matrix dot pushback. And what is pushback expect? It expects another vector. So maybe we say vector row, a vector of integers, row 1, and we say row 1 dot pushback 1, row 1 dot pushback 2, and we push back row 1, and we could make some additional rows, row 2, row 3, row 4, and then we could use a loop. So let's make one more row, vector of integers, row 2 dot pushback 3 and 4. and then push back that row. So for the elements, which are integer types of the dynamic matrix. So you can see this is a vector of integers. We say cout dynamic matrix dot so if we try to print the element is a vector, so we would want to say element dot. Let's not use a range-based for loop actually. And I equals 0, I less than dynamic matrix dot. Okay, just needed to take a second to remind myself of how that works. Printing a vector of vectors, the contents of a dynamic matrix. So if we push back 1 and 2 in row 1, we have 1, 2, and if we create a second row, we have 3, 4. So of course this looks like 1, 2, 3, 4. So after pushing back these rows into the matrix, we expect to have a matrix that looks like 1, 2, 3, 4. So we could use a nested for loop, and if we start at I equals 0 and run until dynamic matrix dot size. So dynamic matrix dot size is going to be equal to the number of rows in this matrix, which is 2 because we push back 2 rows. And in the inner loop, it's a little bit tricky, so I just wanted to pause there for a second to remind myself. We use an inner loop counter variable j, and we loop, and this is the somewhat tricky bit of syntax. So each row's size, and that allows me to potentially have a rows of different numbers of columns. So that's a neat thing. Let's test that in a minute, but for the moment, let's just see that this works. Cout dynamic matrix at position ij. Expect to see 1, 2, 3, 4, and we do. So let's push back 5 here as well. Row 2 dot push back 5. So this is no longer going to be a square matrix. Gonna have the value 5 here. It's an interesting situation. It's not a square matrix, and it's also it's jagged. There's no element right here, so this is a neat situation. So 1, 2, 3, 4, 5, and if we wanted to update row 1 to only include 1 element, or maybe we put 4 elements here. Row 1 dot push back. This is some fairly neat stuff we're doing. This is very dynamic. And if we were to attempt to do this with static arrays, C-style arrays, this type of stuff, and we wouldn't be allowed to change these values and push in arbitrary numbers of elements like we can in this case. We could copy, and change these values as we like, and there's some nice freedom here. So, okay, hopefully that makes some sense. And we can push back additional rows as well. We could print it initially. We could, let me just pause for a minute. So let's create another row. We'll say a vector of integers, row 3 equal. And is this something we're allowed to do? Let's see. So the initial contents are 1, 2, 44, 97, 117, it's at 2, 3, 3, 7, etc. Okay, that's row 1. Row 2 is 3, 4, 5. Okay, and then we printed the initial contents of the matrix, and then we made a third row, and we go 1, 2, 3, 4, 5, and we push that back as well. So, yeah. Again, we could use pointers to pointers like this to do the same type of thing we're talking about here, but the notation gets a bit unpleasant. So if you have desire to do the type of thing that I just did, I would recommend using vectors instead of pointers to pointers. Although people who wrote in the C language back in the day probably used this approach. The only option they had was probably to use this approach. It makes sense, and it can be kind of fun to play with this, but I'm not getting into it. All right, so that's a good point to end this video. I suspect it's quite a long video. Next, we'll get into returning a pointer to an array, which is a way of returning multiple values from a function. It may seem very limited because so far we've written functions that can return a single integer, but if we were to declare like return 5, but if we were to attempt to return to make some array consisting of 10 elements, and we attempt to return some array, this will clash. So return value does not match the function type. It's going to return an address here. So not typically nowadays we would return a vector of integers, but you can also return a pointer. That's a way to return multiple values from an array. So we'll get into that next time in the next video.